Hey everybody, it's Mr. Spudik once again. Today we are talking about impulse. Okay? Impulse is a nice way to go. Sometimes teachers will go from momentum to forces, and in between, the little segue will be impulse. You might have a different order of things, but it really ties in momentum and force together. Okay, so let's talk about what impulse is to start with. And I forgot. If you have not learned about force yet, some people do momentum before force. If you have not learned about force yet, okay, you do need to know the units for force. The units for force are newtons, named after the fig. Oh no, yeah, you're right. Yeah, Sir Isaac Newton. Okay, that's my joke. All right, so 1 Newton is going to be 1 kilogram times 1 meter per second squared. All right. And that will kind of show you, if you have not learned about force yet, if that's the units for force, you might be able to try to figure out what the equation for force would be, given the units kilograms and meters per second squared. But I'll let you worry about that later. Okay. So let's talk about what impulse is now. Impulse is the change in momentum. Okay, think about what that would be. If an object is traveling along, it has a mass, it has a velocity, it has a momentum. All right. Now, if we have that object stop, the velocity is going to change. All right, so you have this change in momentum. So impulse is a change in momentum. Now, we've already been given this formula before, momentum, and we use the letter P for momentum. Even if you have not seen momentum yet, we are going to use the letter P for momentum. All right, now, I want you to think about chemistry class. If you learned in chemistry, was there a symbol we used for the change in? All right, delta. So, delta, or the triangle before the P, will mean the change in momentum. So delta P is a symbol. We actually don't give it a new letter. We're not going to use the letter I for impulse. We're going to still say it's momentum. It's still momentum. It's just the change in momentum. So we will use the letter delta P, or that symbol, for impulse. Okay, so what's interesting about impulse is there's actually 2 different equations. Okay, so here's your first equation for impulse. Impulse is equal to mass times change in velocity. So going back to the scenario, right? We have an object that's moving along. It has a mass. It has a velocity. That, let's say it hits a wall. Well, the velocity was some value and then it stopped. So you have a change in velocity. Mass won't really change. The velocity will change. Okay? So, the first equation we have is impulse is equal to mass times that change in velocity. Now, there's another equation for impulse, though. Impulse is also force times time. So, let's say I have the object and want to throw it again. Okay, let's say it's a baseball. I'm going to throw that object. I'm going to apply a force to that object for a certain amount of time. Okay? And so if I apply a force for a certain amount of time, I will give that object an impulse, which will end up giving it a velocity. Okay, but the force times the time is the impulse. Now, if you think about it, if you've ever played sports, okay, when they talk about passing a ball or a hockey puck, whatever, they always use the word follow through. Okay, they always have that phrase. So when you throw a ball, they want you to follow through. Passing a basketball, same thing. Follow through. If you think about this equation for impulse, what they're actually just asking you to do is get a greater amount of time, okay? Because the bigger time you can give it, the bigger impulse you will give on that object, on the ball or whatever. Okay, so we have 2 equations for impulse. Impulse is mass times change in velocity, and impulse is force times time. Now, I could ask you, or your teacher could ask you, what is the impulse of this? What is the impulse of that? And that would be very boring, but we could ask you to do that, and you could calculate that. I give you a mass, I give you a change in velocity, you calculate impulse. Okay, I give you a force in newtons, and I give you time in seconds. And I say calculate the impulse, and you can do those. But that's not the key, and that's not what's interesting about impulse. What is really interesting is the fact that we can set those two equal to each other. Okay, if we know that impulse is equal to mass times change in velocity and also equal to force times time, we can set the two equal to each other. So mass times change in velocity is equal to force times time. Okay, let's have a scenario. Let's say that I'm going to run, and I have a mass, I have a velocity, and I'm going to go run into a wall. Don't ask me why I'm running into a wall, but I'm going to do it anyways. Okay, I run into that wall. That would hurt. What happened? Why would it hurt? Well, if I'm running into a wall with no padding, I'm going to have my mass and my change in velocity. Okay, my change in velocity is going to go from whatever velocity I have to 0. Okay, so I'd have some type of velocity there. Now, on the other side, so this mass times change in velocity would be pretty much set. Okay, no matter what, I have the same mass, and no matter what, I'm going to end up stopping with whatever velocity I have. So I have a set impulse. However, if I just run into a wall with no padding, I'm going to have a very, very small time. And if I have a very small time, I'm going to have a big force, which is why it hurts. Okay? But what if I run into that wall, but instead I have a lot of padding? Let's say I have a bunch of mattresses stacked up against this, on their side, stacked up against the wall. And then I run into it. I still have the same mass. Okay, I still have the same velocity. I'm still going with the same velocity I went before. I'm still going to stop. So my mass and my change in velocity are still set as the same. But this time, when I run into those mattresses, it takes a longer time for me to stop. Well, if it takes a longer time for me to stop, I've increased my time. So my time has gone up. That means my force will go down. Okay, so the phrase you need to know, or sentence, whatever it's going to be. When the time goes up, the force goes down. Everybody say it with me. When the time goes up, the force goes down. I didn't hear you. Try one more time. When the time goes up, the force goes down. Better, but we need to work on it. Okay. All right, so when the time goes up, the force goes down. This concept, okay, it was really basic algebra. Okay, this is not big algebra. Yeah, you can use this equation a bunch, and really, you're going to be given, if you do much calculations with this, you'd be given 3 variables, and you'd have to solve for the 4th. Okay? But this is a very strong concept in physics. Okay, think about sports. Where do you see this application about increasing the time to decrease a force? I'm going to say everywhere. Okay? I want you to think about a football player. Okay? A football player, when they catch, if you watch any football players warming up before a game, you will see the wide receivers really exaggerate their hands to catch the ball and receive the ball. They'll have their hands out here, right? They're supposed to catch and have their hands out, and they're going to be bringing those hands in. If a wide receiver tried catching a football like this, okay, and they didn't bring their arms in, they would have a very, very small stopping time. The time did not go up, okay? So they tried catching here, the time isn't going up, the force will be too great, and it'll be hard to catch that ball. So they exaggerate. They exaggerate especially when they're warming up. They want to increase the stopping time to decrease the force, okay? Soccer players, when they get a ball hit to their chest, they're going to give in a little bit. Okay, that ball hits their chest. If they ran around like this, let the ball hit their chest, it would bounce off their chest and go to somebody else. So when the ball hits their chest, they're going to give. They're going to increase the stopping time to decrease the force. Okay, same with a foot trap with soccer, same exact thing. I just can't show that from here. Okay, but their foot is not going to just be held out there or it's going to bounce off and go to somebody else. They're going to increase the stopping time, decrease the force. Okay, I'm sure any sport that you've played, okay, you could see somewhere where you increase the time, to decrease the force. Okay? Or just within pads. Okay? If you have pads, it's going to do the same thing. Increase the time, decrease the force. Okay? So there's one application with sports. You will see it all over the place. There's points where you're going to increase the time, decrease the force. What about cars? There are a bunch of examples with cars. Okay? First example would be airbags. An airbag is designed to increase the time and decrease the force. An airbag is not designed to inflate and stay inflated. Okay, the problem with that is this. If an airbag inflated and stayed there, if your head hit the airbag and it stayed inflated, then it would bounce off the airbag. Okay? That's not good because now you're doubling the force being applied to your head. Okay? What you want that airbag to do is inflate, and as soon as your head hits it, it immediately is already starting to deflate down to nothing. And that's what an airbag does. It will inflate and immediately start to deflate, so it just slowly brings your head to a stop. It's increasing the time to decrease the force on your head. Okay? If you've ever seen a stuntman or stunt woman, sometimes they have a stunt where they'll jump off a roof. Okay? And they have these big airbag pillows. Okay? The same idea. Those big, huge air pillows will have flaps that shoot out. Again, if they didn't have the flaps that shoot out, they would bounce on the air pillow, then bounce off the air pillow somewhere else. That would be pretty bad. Okay, but also, even if they were just bouncing up, if they had force being applied to stop and then go the opposite direction, that's twice as much force, and you don't want that. So air pillows are set so that as soon as they hit it, the flaps open up and they're just slowly brought down to a stop. Okay, another example of cars and increasing the time to decrease the force, this whole idea of impulse, is that your car is not built to be a tank. Okay, your car is designed to crumple. They call them crumple zones. All right, and you hear people sometimes still say, "Oh, I want a car built like a tank." You know, your parents, they want you to be safe, so they might say, you know, I want to get a car that's going to be built like a tank. Yes, we want to be safe, but believe it or not, cars that crumple and know and plan how to crumple are much, much safer. Okay? I urge you to look on YouTube and watch a video about the 1957 Chevy Bel Air compared to the 2007 Chevy Malibu. And what they did was they had those two cars go head on or a little bit offset, but they went in on a collision together. And you think about these old cars, they were built like a tank and they were big and strong. And those cars in the 1950s had tons of things wrong with them for safety. But one thing was they didn't know how to have a crumple zone. They didn't plan for anything crumpling. Okay? Where now, and they showed the Chevy Malibu was designed, and so the front of the car had already a plan to crumple in an accident. What's the concept that we're teaching? Impulse. So that crumple zone was increasing the stopping time and decreasing the force on the rest of the car. And so the front of the car and the rear of the car, of any car now built, will have crumple zones so that anyone in the passenger area will be safe because it'll take on that impulse. It'll increase the time, decrease the force on that car. Okay, one last example of increase in time, decrease of force is something you will probably see now on the side of the road all the time. Okay, anytime where you see a divider, you're pulling off an exit. Okay, you will see these types of things. You'll have something on the end of that divider, and believe it or not, those are built to crumple as well. Okay, those will be designed. You might see just like the pictures here. Okay, you might see some with barrels or whatever, and it's because if they have something that's hard, a hard concrete divider, they don't want any cars going directly onto that. So they will build onto it things that are going to crumple. Okay, so if you look at the picture up top to the left, right, this is a design that will show that guardrail is going to actually shoot off to the side. Okay, and these, okay, will have possibly air or water or something in those so that it will handle and it will increase the time to decrease the force. Okay, that's it for me and Impulse. Thanks so much for watching, and I'll see you later.